once again, I think we are making good progress. I really want to bring to the fore the progress we've made so far, and I hope that we are working together. I think the previous lesson we discussed 3D objects and camera models and camera control. That is in lesson 7. It was actually the previous lesson. If you look at the progress we've been making, you see how interconnected these lessons are, and I'd just like us to have a look at that. So we moved from lesson 1 to 3, where we dealt with introductory issues, and we introduced WebGL before we got to lesson 4, where we dealt with curves, and together with curves we also came across the issue of polygon meshes, polygon soups and meshes, which are critical for introducing 3D shapes, eventually 3D objects, and transformation. Polygon mesh eventually gives birth to 3D objects, and without the transformation, it doesn't become very practical for us to be able to, change the views of the of the 3D objects in the three-dimensional space. A good example is what probably we would see in this polygon mesh. This is a dolphin that is presented using a triangle mesh. You can see it's a series of triangles all over that is presented there, representing the dolphin. But of course there are some lighting effects. This is why all these are interconnected. The reflection on the surface giving, and you can see darker, lighter shades, reflection, more reflection here. This gives a 3D effect on the image. So today I would want us now to focus on the visibility, lighting, reflection and shading. And of course you can see that from this diagram the impact of 3D is created more by the lighting and shading effect. The reason why we are discussing visibility, lighting and shading is because, of course, after we do the 3D objects and we have done the cameras, now the cameras, while doing their jobs, cannot perfectly do it without looking at the sources of light. I mean, in real life, even when you're taking a photo, you get concerned about the source of light, otherwise it will destroy the image. The image that will eventually be produced might have too much reflection, such the ambient or the backlight is not adequate for the effect of the image to be seen properly, and we say your photo image maker. So sometimes even when you're taking photos, we tell people, now you can't sit there, we sit because the direction of the sun is here. Even in virtual cinematography, these are real concerns. What is the source of light? What is the nature of the surface, the texture? How much of that light is it reflecting? What type of light is it reflecting? So these concerns become real. If we have to make those movies almost like real movies, the ones, the animations, even the adverts, then we've got to get concerned about the visibility, lighting, reflections and shading. Just to give ourselves a better hint of the same, let us look at this lighting. Is this a plate or is it a ball? Now the difference between the answer to that question depends on which image we are looking at, because there are 3 images here. The first image consists of what you're going to later to see is called ambient light only. The second image consists of the ambient light plus a little bit of the shininess you're seeing here, specular lighting. The third one now has 3 aspects, as you're going to be seeing soon. That is why by the time you get into the third one, we can correctly say this is a ball, probably on a field. Excuse me. So the first one looks like a plate, but the third one looks like a ball. The difference is in the lighting and shading. That is the importance of this unit that you're calling visibility, lighting and shading. And as you're going to see, we will know that physically objects can be said to have the color of the light that they leaving the surface. So if we have an object that we see as green, is because the color that is leaving that surface, if white light bounces on it, if white light shines on it, whatever bounces out of it is a green light. The other colors are absorbed. So that means we see the light that is reflected. Hence this one may be a little bit confusing now when we think of it's not white light that is being shined upon the object, but blue is a blue object with which is being illuminated with red light, what kind of light are you going to see? What will be reflected? Will it be dark? It's supposed to absorb every other light and reflect blue. So will it absorb all the red and reflect? There is no blue to reflect. Is there blue in red? Anyway, so these are some of the questions that can be answered in this unit. Our objective in this unit is to understand and model what light does into a scene, and you're going to be seeing that. We are going to see that we have three major types of shading. We have flash shading, we have ground shading, and Polygonal shading. And you're going to see that Opengl makes use of flash shading and also of ground shading. I'm referring to this flash shading and then ground shading. I think it's yeah, this ground. I don't know how to pronounce this. Guarad shading or something, and then Polygonal shading. So, which you're going to be. You may not have the time to look at it intensely, but I will share this content so that if you have the time, you can have a look at it. And as you can see in flash shading, we see the boundaries here, because each the human eyes are able to access to discover the discontinuity at the boundary. That is the flash shading. Every polygon here in this polygon mesh is given a flat shade, the same color. Now that we'll be able to see where the boundary is with the human eye. To remove this, that is what is addressed. We call it the match bar effect. To introduce that smooth shading is when you have the garage shading. As you can see, garage shading here. It fixes the match bar defect and removes the edge discontinuity. Your eyes will not discover that you have several polygons making up this shape. Polygonal shading, okay, garage shading works so much well on the vertices, and so that you're not able to see the edges, but then is a little bit poor when it comes to the lighting, and especially when it comes to specular light. Polygonal shading exists for that purpose, so that you can be able, because Polygonal shading focuses on each of the pixels, and therefore you can see the specular light is more visible in Polygonal shading than it is in garage shading. Now in garage shading is used by Opengl, but Polygonal shading is not in Opengl. Probably in future versions we are going to have it. So as you can see now, when you apply garage shading which is the default used in Opengl, then we can see we just need to insert the primitive GR smooth, and then we have the parameter there, and then you have the smooth image. Now this one is the same image here, but this one applies flash shading, and this one has applied Gora shading. So there is a lot more that you're going to be looking at. These are just some of the properties of Polygonal shading. But in this particular unit, as we have done in this particular lesson, as we have done in the others, we are going to focus more on the concepts. Like I said, computer graphics can be very wide, but if you deal with the concepts, even if you read the other materials, you're going to connect the concepts, and then you're going to appreciate. So we're going to look at very briefly visibility in graphics theory. What does that mean? And visibility in Opengl, we have seen we apply garage shading, simple reflection models, lighting in Opengl, flat and interpretive shading, as well as we have already seen the flat. Excuse me. We have already seen the flat shading. We're going to be looking at interpretive shading and shading in Opengl. We have seen the garage shading that is used in Opengl. About 4 pages of that will be adequate for the concepts. Well, visibility in Opengl. The correct visibility is when multiple opaque polygons cover the same screen space. And only the frontmost one is visible. In other words, we remove the hidden surfaces. Otherwise, in the presence of hidden surfaces, that's wrong visibility. It's weighty, it overexploits the resources, it is not needed. Now, visibility in Opengl, Opengl directly supports depth buffering. We have to remember that with graphics we have a buffer, and this is physical buffer. It exists. It's a memory that holds the image before it is displayed on the screen, and has depth buffering, which brings about the impact of the 3 dimension. So Opengl directly supports this depth buffering, but it is often used in addition to other visibility techniques in interactive applications. For example, many games use a BSP tree to prune the amount of static map geometry that is processed that would otherwise not be visible anyway. Also, when dealing with blended translucent materials, these objects often must be drawn from back to front without writing to the depth buffer to get the correct appearance, so that you can be able to see the item through the translucent material. For simple scenes, however, the depth buffer alone is sufficient. To use depth buffering in Opengl with the Graphic Library Utility Toolkit, the Opengl context must be initialized with memory allocated for a depth buffer. With a command such as the GL Utility Toolkit, initialize display mode, that is with the with the primitive glad RGB, glad double, and glad depth, either of them. Next, depth rating and testing must be enabled in Opengl. How do you enable it? Remember, to enable these primitives in Opengl, we use GL enable, and then we specify the depth test. Opengl will automatically write pseudo depth values to the depth buffer when a primitive is rendered, as long as the depth test is enabled. Now, the GL depth mask function can be used to disable depth writes, so that depth testing will occur without writing to the depth buffer when rendering a primitive. When clearing the display to render a new frame, the depth buffer should also be cleared. And we have seen that we had this GL clear, we have used it when you are learning about the 2D shapes and WebGL. We use this GL clear to clear the buffer, so that to allow for a new frame to exist. In a way, we can clear in the canvas. Now, we have a look at simple reflection models. Surface reflection depends on both the viewing and illumination direction. So, which direction is the light coming from, and where is the viewer? In this case, in Opengl, we place the viewer with a projection plane, and a simple reflection model would be dichromatic reflection, meaning we have like two colors, like this observed image here. You can see we have the light source here, we have the viewpoint here, and we have the highlight here. This is the body color. Of course, this shows the specular reflection here. It does not specify any specific model for diffuse or specular reflection, but as you can see, it's visible to us that there is some level of specular reflection and also diffuse. Lighting in Opengl provides functions. Opengl provides functions for setting up point light sources and spotlights, selecting surface reflection coefficients, choosing values for several parameters in basic illumination model, and it implements the point reflection model. Steps in Opengl lighting. Actually, it implements the Garrod reflection model, not the point. That correction needs to be made. Steps in Opengl lighting. 1. We enable the lighting and select the shading model. Then specify normals, specify material properties, and specify the lights. When you enable lighting calculation, globally by opening the GL program using this GL enable, like I said, GL enable is used to enable these primitives. In this case, GL lighting. Once lighting is enabled, GL color can be ignored, and enable individual light sources also. Up to 8 light sources are available in Opengl, and that may be grown further, but the default ones are 8 of them. Some manipulation may allow more than 8, of course. We have, it starts from GL light 0 to GL light 7. GL light 0 is one that is fully defined. The rest are all defined to, like, they're coming from one side. As you're going to see if you investigate further, you're going to see the parameters that are used with these ones. Beyond enabling, then have indicate that is only the first one probably that has the white light shining on an object. Okay, in Opengl, a viewer is replaced with the projection plane. I had mentioned this. We replace the viewer with the projection plane, and rays which reach the center of projection. COP stands for center of projection. After passing through viewing plane are actually seen. Color of pixels is determined by our interaction model. Now we have limitations of Opengl lighting. 1. The pipeline is essentially one way, left to right. Once a polygon has been rendered, it's forgotten that it cannot be used as part of any other lighting calculation. It's rendered. It's seen on the screen. That's it. It's done. No mirrors, glow sticks, made with emissive light won't actually light up anything else in the scene. You don't have real mirrors. Emissive light, what you use is emissive light. Can only capture light source. Light source that is light source that is tied into. You have light sources, of course. We have 8 light sources, 0 to 87, and you can increase more of them. Now, so these are the limitations of Opengl lighting. And as we discuss lighting further, probably in the I'm going to do some further discussion on the lighting. This may sink, and you're going to see how it impacts on Opengl and computer graphics in general. But the other solutions out of Opengl that are still used in computer graphics, it's not like computer graphics is about Opengl alone. Now, flash, when it comes to shading, we can have flat, garrod, and Pong shading. Here we're discussing about flat and interpretive shading. The flash shading is the simplest, cheapest, and fastest shading method. Why? Because it just gives the same color to the objects. It doesn't create any 3D effect. It's almost like ambient. Now, works well for objects really made of flat surfaces. Appearance depends on number of polygons for curved surface objects. Fuse an entire polygon with one color intensity. This model is only realistic if the light source is imagined to be at infinity. The viewer is at infinity. The polygon is not an approximation of a curved surface. Ideally, I have to have indented these three to enhance readability, but now that you can view this video, you know that these three fall under these 3 points fall under this model is only valid if 1, 2, 3. Now, flash shading in Opengl is specified using the GL shade model, but with the GL flat constant here being specified. The color at the first vertex will determine the shade of the whole polygon, so you don't have to go trying to specify the color at other vertices. Once you specify the color at the first vertex, that covers the entire polygon. Flash shading suffers from much bad effect. We've already seen that, where human eyes are able to detect where the boundaries are. Now, interpretive shading is the idea of avoiding when you're using interpretive shading, you're trying to avoid computing the full lighting equation at each pixel by interpolating quantities at vertices of the faces. There are 2 methods which can be used for interpretive shading. Those of you who have done maths, they know about interpolation and extrapolation. Interpolative means that it is within these polygons that we actually within these bigger images that you're trying to extend the shading effect so that to eliminate the boundary which is visible to the eye when you're using flash shading. Garrow shading, in it we have the radiance values are computed at the vertices and then linearly interpolated within each triangle. For Pong shading, the number values at each vertex are linearly interpolated within each triangle and the radiance is computed at each pixel. We see that Garrow shading is more efficient for purposes of rendering, but Pong shading is more accurate. I think that can be described very easily using one of the diagrams we came across. I think probably we can have let's see whether we can see that here. Yeah, this is it. Garrow shading and Pong shading. Because here we target each Pong is able to target each pixel, but it's computationally very intensive. The amount of computation that has been done is a lot. It slows down the process. Therefore, Garrow shading is said to be more efficient. But this one, as you can see, is more effective. The impact is clearly seen, is more accurate. You get a better graphic. You say therefore Garrow shading is more efficient, but Pong shading is more accurate. Opengl only directly support Garrow shading or flash shading. It doesn't support Pong shading. Garrow shading is enabled by default, computing vertex colors and interpreting colors across triangle faces. Flash shading can be enabled with GL shade model when you specify this attribute to be GL flat. This renders an entire face with the color of a single vertex, giving a face red appearance. With pixel shaders on programmable graphics hardware, it is possible to achieve point shading. Of course, to achieve point shading by using a small program to complete the illumination at each pixel with interpreted normals. It is even possible to use a normal map to assign arbitrary normals within faces with a pixel shader using the normals to complete the illumination. In other words, it's possible to mimic what we have in point shading by using what is provided in Opengl flash shading and Garros shading. So just to add that a little bit to the concept that we have just gone through, because the rest here is a discussion topic, is probably visit this. We say that our intention here is to understand and model what light does in a scene. And we can quickly see a model of lighting where, even if we were to go a little bit back, we can see that we can be able to, is this a plate or a ball? Back to this question we asked in the beginning. We say the difference here is in lighting and shading. The first one only has ambient light, the last one has ambient light, specular reflection, yeah, and you can see. So it has more than just ambient light. So the physical reality is that as light hits the surface, part of it is absorbed and part of it is reflected. Visible light includes all colors of the rainbow. And objects, of course, are seen based on the light they reflect if the surface absorbs the rest of the light present in the white light. Whatever is reflected is what we are able to see, and we are able to say is the color of that object. A model of lighting such that it follows are rays from light source. This is a light source. Only light that reaches the eye is ever seen. We don't see light that doesn't reach the eye. Direct light is seen as the color of the light source. Direct light of the color source. Indirect light depends on interaction between the material and the light. This material and the light. So this person could be seeing white light from here, and he could be seeing this as light blue. And in computer graphics, we replace the viewer with a projection plane. So if you look at this graphic and what we have here, we are saying this viewer in computer graphics. Remember, we are talking about virtual cinematography. We replace that viewer with this, which is called the projection plane, and this is the center of projection, the equivalent of where the eye of the viewer would be, for instance. Now rays will reach the center of projection after passing through the viewing plane and are actually seen. Color of the pixels is determined by interaction model. Light material interactions determine whether an object appears red or brown. The way light interacts with the material, does it appear red or brown, light or dark, dull or shiny? This is an issue of interaction between the light and the material. A reflection of light from a surface can be either specular, I just mentioned about that, specular, shiny speck, if you want to interpret it that way. There is a shiny speck here because this material is specular. This material diffuses the light. The light seems to leave the surface reflected in all directions, equally in all directions. It could also be translucent. It fails to reflect all the light, allow some of it to go through. Actually, objects below can be seen, but not very clearly. That's translucent surfaces. Specular surfaces, of course, you can see, this is an example of an image, is mirror-like, and the reflection is focused on one direction, what we call the angle of incidence or angle of reflection. Diffuse surfaces, like I said, light is reflected almost uniformly in all directions, as shown in this particular image. Translucent surfaces, they will allow some light to pass through. You have like glass or water-like. Then you can say that the light material interaction, or that is interaction of surfaces with the light, can be specular, diffuse, or translucent. A surface is never perfectly diffuse or perfectly translucent or perfectly specular. That's obvious. It may have all these properties. To model these properties, we must understand how light reflects off each of these surface types. So we adopt illumination models which you consider a basic illumination model which gives reasonably good results and is used in most graphic systems. The important components are diffuse reflection, specular reflection, ambient light. Example, here we have specular reflection, we have diffuse reflection, and then you have ambient light, that light that appears to illuminate something behind the light source. Yes, this is what you are talking. If you walk around the box and the light source is here, what you see on this side, if you can see the back face, this type of indirect light is what you call ambient light. So these have ambient light only, since you're seeing them from the other side of lighting. It's called background light. It is implemented in most graphic tools, including in your TV. If you have your TV, you go to the menu, you're going to see something called background light. And actually, when you start changing that background light, you can start seeing something like this. The contrast reduces, the object starts looking darker, and the shining effect is removed. As you move more towards, as you reduce the background light, you are tended more to the ambient light only. It is not created by any light source. It's a constant lighting from all directions, and is contributed by scattered light in a surrounding, and when used alone does not produce very interesting pictures. Indeed, they look like two dimensions. You can see here. These are the RGB consideration for ambient light. We have the reflectance factor, and you have the intensity factor, and the reflectance factor. They must be very poor for ambient light, and you can see we have this material color, we have the light color, then this is the result of ambient light. Diffuse reflection is where light is scattered in equal intensity in all directions. The intensity factor. We go to the surface normals. We go back to the issue of points and matrices and so on. We want to avoid too much mathematics at this level. You can dive deeper once you understand the concepts. We have the light source here, and you have the unit vector that is normal to this surface. This is used in computing the reflection. But again, you can have time to go through that. And of course, the intensity the intensity factor reduces with the direction of the surface. That's why the surface normal becomes important in computing that. You can see the light source, the surface normal. So as zeta increases, the brightness of the surface decreases. By what? So that's when we now call working with the dot product, and we are able to discover what happens and the impact that has on brightness. So these are diffuse reflections at different levels. So at this at 0, we only have ambience, 0.25, 0.5, 0.75 at 1, diffuse reflection, or reflection almost equal in all direction. Of course, if we add the diffuse reflection on the ambient light only with diffuse lighting, then this is what we have. We can see some 3D effect coming into place just by lighting using diffuse lighting. What is lacking now is that we don't have the specular reflection. With specular reflection, we have the white specular highlight, shiny surfaces. Intensity depends on where the viewer is. You can see this image. This tells us the light source could be from above, because the specular reflection here is on top of each of these objects. The ambient light is at the back, therefore this light source should be from above of the objects as they are placed. So again, I want to avoid these computations and explanations so that to make it more palatable for us. So with the same image we had earlier on, if you illuminate specular lighting, then you can see the effect ambient plus diffuse. Plus if we have this as a material color, the light color as white, then we introduce specular. If specular reflection, this is what we have, and then if we combine the ambience, diffuse and specular, this is the kind of object that we end up having. So you can see these are for specular and diffuse only. Of course, when in the absence of the two, we have what we call ambience. The form reflection model, remember we had mentioned about it as one of those that is not supported by Opengl, but can be mimicked in some way through computations. Due to the ambient light, nothing can be entirely black for form reflection. Mirror reflection are possible in form reflection, can be computed very fast using the in VR and games. Very good approximation of diffuse surfaces, physically inaccurate, expressed in terms of vector geometry. Of course, if you now put all of it together and combine the diffuse 0.2, 0.4, 0.6 at specular at this level 0.20, at the increase the specular aspect, here shyness, you can see the impact of the various graphics presented there. Opengl lighting functions, we have seen some of them in the content that I just presented. When you're doing lighting in Opengl, you have to enable light and select shading model, specify the normal, specify material properties, specify lights. We say there are 8 lights, so that's the same story around here. As you can see, geo enable lighting, ignore color. I think we have said that we don't have to go through this. We have also seen this probably towards the end. You can see summary of polygonal shading, curve shading, set vertex normals, calculate colors at vertices, interpret colors across polygon, must calculate vertex normals, must normalize vertex normals to unit length. Pong shading creates greater realism than curve shading. We say it is more accurate, but it's computationally intense. Remember I mentioned it involves a lot of computation, and therefore it's not supported by most graphics hardware. Of course, nowadays you're having very advanced graphic hardware to deal with that. No wonder when you want to buy computers for computer graphics, we buy the ones with advanced graphics cards. That's the idea, so that we can be able to support Pong shading and other complex or computationally intense solutions in computer graphics. Thank you so much for attending to this lesson, and I'll be now combining this lesson and the previous lesson and make a quiz out of it, just to see to it that you are good to go in terms of understanding the concepts related to visibility, lighting, and shading. Key among them is the difference between flash shading, garrow shading, and also the issue of Pong shading. We have also seen the issue of surfaces, the kind of surfaces we have, and we have seen the issue to do with the lighting effect based on those surfaces, the source of light and the viewer. And you have seen that the viewer is also replaced by the projection plane, where the center of projection becomes like the eye of the viewer. So thank you. Let us now look forward towards the quiz, so that you can test our understanding of these concepts. If you find yourself not grasping this concept at the first instance, don't worry. You read the first instance, then revisit it later. You're going to start seeing the connectivity among these the various connectivity between the various concepts. Thank you.